Okay, so this is team challenge number 12, which is the Lineweaver Burk plot, a type of question you will always find on the midterm and the final exam, so good to know how to do. So what I did was I took the numbers from the table on the team challenge and I put them in red in this table, and I've also just sketched out a little bit of a graph for myself to work on. The first thing you always do in this is it's a double reciprocal plot that we're looking for here. So we're looking for a 1 over V naught on the y-axis versus 1 over S on the x-axis. So the first thing to do is to calculate the reciprocal 1 over S and 1 over V naught. Usually I give you lots of room in the table to do that. That's why I put so much space there, so you can get your data in. Once the data's there, I think it's a really good idea to then set your graph up, because a lot of people have trouble plotting Cartesian coordinates, strangely enough. So by that, what I mean is, look at the first point. It will be the largest 1 over S naught and 1 over V naught, because it is the smallest S naught and S and V naught. So I have 0.4 as my top point for 1 over S. So I am going to make that over here on my x-axis, which I am going to label concentration of 1 over the concentration of S. So the unit will be in 1 over micromolar. Okay? Or you could write it as micromolar to the -1. That would work too. Alright, so I'm going to label up my axis so that I have good spacing here. Now I'm putting the 0 partway through the graph, usually about a third of the way from the edge. That's because the x-intercept is going to be an important parameter as well. Okay? Now on the y-axis I need to go to 0.04 and a bit, so I am going to go, this is going to be 0, 1, 0, 2, 0, 3, and 0.04 with the halves in between them. So it's really important to set your axes up in a linear way, spaced evenly across the axis. That's very important. Then I can plot my data. Okay, over at 0.4 and 0.04 and a bit, I have a point here. At, might be easier to use my ruler, at 0.2, I'm at 0.02 and a bit, so down here roughly. It's not going to be the most fantastic plot in the world, but you'll get the gist. At 0.1, which is here, I'm at 0.011, so that's in here. Really a lot easier to do this when you got lines. 0.05 here is going to be at 0.0064. So that's 0.01, that's 0.005, so 0.0064 somewhere in here. I'm actually going to stop plotting now because I can't really do that very easily, but you would fill in the points in here. Alright? Then you take a line of best fit. Unfortunately I'm going to have to do this with 2 goes of my ruler because my ruler's not long enough. I'm going to start here. If my data's not perfect, I just do the best I can. Okay? And I'm not going to get fantastic accuracy on this board, but anyway, I'm going to try. Really seem to be covering up that point there. It's going to be something like this, okay? Hopefully when you have good graph paper you do a better job. The key parameters are 1 over V max, which is here, and -1 over Km, which is here. That's going to be really hard to read off this graph, but I'll do my best. 0.005 is here, so 0.0025 would be there. This looks to be about 0.002 as 1 over V max. And it looks like this is 0.05, and that's -0.05. This looks like about -0.0, that's 0.1, so that's 0.05, so that's 0.02 is equal to -1 over Km. So if I figure out the reciprocals there for this badly plotted version, I have, let's see, 0.002, 1 over x. I get a Vmax of 500. The actual data here, if you plot it out properly, you will get a value of 666, okay? So actual Vmax equals 666. And the Km here, I get a value of 0.02, negative 1 over x gives me a Km of 50. Okay, so we have our values obtained from the graph. It's really important that you get the values from the graph. Okay, you can also use the slope, which is equal to Km over Vmax, to determine those parameters as well. The next part of the question asks you for what the kcat is, given in the first part that it's an 11 nanomolar solution. So we know that Vmax is equal to kcat times ET, the enzyme concentration. So kcat is going to be equal to Vmax divided by the enzyme concentration, which is, now we've got to be in the same units of concentration here. So I'm going to take my 666, which is the actual value, and convert that, that's in micromolar per minute, convert that to nanomolar per minute by multiplying by 1,000. So I'm going to say that kcat is equal to 666,000 nanomolar per minute divided by 11 nanomolar ET, which gives me a value of 60,545 nanomolar, or no, 1 over minutes, sorry, cancels, 1 over minutes. If I want to make that into seconds, I have to divide this by 60 seconds per minute, and I will end up with a turnover number of 1,009 1 over seconds. So 1,009 turnovers per second. The final part of the question is to find what the V naught is at a different enzyme concentration at a certain concentration of substrate. And to do that, what you need to use is the Michaelis-Menten equation. I'm just going to work over here. V naught equals Vmax times S over Km plus S. Now, important to remember that Km is a constant, so we'll just use it the way we derived it. S is given in the question. That is 66 here, micromolar. This is 42 micromolar. And Vmax is the thing we have to calculate freshly here, because we're at a new enzyme concentration, so we need a new Vmax. To calculate that new Vmax, we just use this equation that we used before. So it's equal to kcat ET, which is 1,009 per second, 1 over second, times our new concentration, which is 31 nanomolar. So that gives us a Vmax, which is 31,279 nanomolar per second. And if I convert that to micromolar per minute, it ends up as 1876.7. If I put that back into that equation with all those numbers, I'll get a V naught that is equal to about 1,147 micromolar per minute. So the key things in these types of questions, it's all about good plotting. You have to properly plot and label. I have not done that. 1 over V naught here, which will be in minutes per micromolar, okay, as a unit, or micromolar per minute to the -1, whichever you like, and to carefully plot in a very linear way, and this will all work out for you. Okay, so that's team challenge number 12.